so welcome everyone. We're going to try something different today. I haven't done this at all during the course because I tend to find it's not that useful, but given that it's the wrapping up and I did want to cover these ideas, I wanted to go through a live kind of coding demonstration of me walking through a data science problem. And I'm going to write the code. That's actually the most inadvisable part probably. I probably should just be copying it, but I've always found that when I just see someone sort of run cells in a notebook, I don't have any insight, whereas typing it forces me to go at a speed where people can hopefully understand what I'm doing. So hopefully, if nothing else, the pacing of typing it will help things a little bit. Before I do that, though, and we'll see. It may go well. I may not get through it. I have my cheat sheet here, so I'm going to be referring to it heavily. But of course, you know, given that I'm following the script here, it's not going to be a precise actual process of how I approach the data science problem, but it's a reasonable approximation. I did this in the span that took longer than this time, but not days. This is a matter of many hours. So hopefully it'll be a reasonable insight, at least into how I approach problems, which hopefully will then be useful for everyone here. One question that was asked on Piazza was about the final video presentations. We're going to post more information about that, or by next Monday we'll definitely have more information. We're still trying to finalize a time and place for that. So it's going to be on the 14th, but we're trying to finalize a place so that everyone can in fact come and attend in person if they want to. Any questions about what's the goings-ons? We finally have the graders up. I'm not quite sure. It just happened, so I'm trying to wait to see if there's any other problems. We may extend the deadline by 1 day for homework 6, just to account for that. But I'm also wary of doing that because then it's pushing up. If you use the late days, then it's pushing up right against the time that the final project is due on the 9th, and that might cause more stress ultimately. So we'll think about that. We'll see if we could even push the project back 1 more day. It's about the amount of time it will take us to grade them, so there's some issues there, but we'll see. Okay, any questions about that? Yeah. So it's sort of funny because it's always about you always have more options when you push it back, right? You can always do it early, but that doesn't really. It's not really how it works in practice, amazingly, right? So I can, and I'm inclined to do that to a certain extent, but also I'm also a little bit hesitant because we all know that it doesn't work like that. And if the deadline is pushed 1 more day, people just say, "Oh, we have 1 more day," and they'll start the next day. For very good reasons, by the way. There's nothing wrong with doing that, but it's just the reality of things. Okay, so let's go through a data science problem. I'll do this fast. Hopefully I'll get through it all. Maybe I won't, but hopefully get through everything. But here's the problem. And again, this has come up kind of at the last minute, so it doesn't. The end result, I'll just preview everyone now. It's okay. It's not great. It's not a super insightful result. That's the issue with data science. You may not get a wonderful, amazing thing you can publish in Science every time you do it. That's like half the time you get that. But let's talk about a data science problem. So as I've mentioned before, I have a young daughter, and I want to buy her a Christmas present for Christmas, right? Christmas is coming up, so I have to buy, or holidays are coming up, so I have to buy her a Christmas present. In our case, it is Christmas. And so I want to know what's a good present to get her. And if you go on Amazon, there's the toys departments here. So there's toys and games. I'm going to look at those. I'm going to look at now baby and toddler toys. So I'm going to look at baby and toddler toys. And there's a lot of options for toys available. I'm going to check her age. She's 2 years old, so I'm going to get 2-year-old toys. And there are some 5,000 of these, I believe. There's 24 on a page. And oops, I actually want it also to be Prime eligible because I want to get fast shipping so I can wait until the last minute if I want to. So there's let's see. It actually just changes, of course. So there's actually more than there were available originally. Maybe I want to have free shipping as well. But anyway, this is sort of the set of things I want to look at. And when I buy a present, I sort of want 2 things, right? I want it to be a present that's going to get good reviews, right? So because you want to have high stars. You don't want to get a dud of a present on Amazon. But as also every parent knows, you don't want to be just a follower either. You want to get a present that not everyone else has, because if everyone else has the same toy, it's kind of a pain. You don't know whose is whose when they have play groups. And so instead, I want to get a present that has not been reviewed very much. All right, so all these toys, they're the featured ones. They'll have tons of reviews. If I buy one of those, it's just going to be one out of every kid that has that, and so that's not what I want. So I want to find the presents that are high quality, but which haven't been yet reviewed very much. Oh, actually, no, I want them. That's right. I want them to be reviewed. I forgot to check that stuff. That's why I wasn't having everything. I want them to be reviewed at least once so that I can train on things, but I'm going to look at eventually the things that have been reviewed very little and see if I can find the gems of that group. So there are a lot of these. There are, I guess we checked, there is some 5,000 some things, 220 pages worth of these things on Amazon, and I want to try to do some machine learning or do some data analysis of this data set. So I'm going to go through kind of how I go about doing this, and we'll see how far I get. But hopefully you'll get some insight into maybe how I approach a problem if we can do it fast enough. All right, so let's get started. So here's our blank notebook. That's how everyone starts. Right? That's how you start your data science. It's a blank slate. And let's start with our from BS4 import beautiful soup. Okay, let's do our normal ones. Import NumPy as NP, pandas. SPD, import requests. What else do I need? I probably want matplotlib. What do I want else?
Regular expressions?
I'm not going to use regular expressions, actually. I'm going to use beautiful soup, so I don't need those. Let's get Seaborn, so I have nice figures. Let's get, I think that's all for now. Oh, and I have to make it inline.
There's a typo at the matplotlib one.
Matplotlib, pyplot as plot. Okay, perfect. Okay, so now I'm going to start at this page here. So I'm going to start at this page, and I'm going to issue a query to get this data here, right? There's my cheat sheet there. Okay, so I have the URL, and I'm going to get this URL, and I'm going to run Beautiful Soup on it. Content, and then I'm going to find the item. Well, I'll just do this first, and then I'm going to look at what root is. Okay, so what's happened here is that Amazon doesn't want people doing this. So by the way, I mentioned this actually because by doing this lecture at all, I'm breaking the terms of service, I'm sure. So when you do this, what you'll find is it says Amazon says very helpfully, if you want to do this, please contact our support system. Don't do this actually. And so it turns out you actually can't. You have to be a little trickier when you do this. So Amazon checks the headers of your client when they see who's connecting to it. And by default, a scraper says, it will say, no, I don't want you doing this. So in order to get past this, you have to look on Google and find a little bit about some headers that let you scrape data from Amazon. So here they are. Here's the headers that I can put in. So again, this is why I probably shouldn't be doing this because it's on film now that I'm in fact violating the terms of service that Amazon has. But I'm also going to say set the headers to be equal to that. And now I'm going to do this first. Okay. So now if I print this, it's a little better, and it looks like an actual. I shouldn't have done that actually because it's going to print the whole page, but it looks like an actual page, and in fact it is a page. Okay, so now I want to start actually getting the content from this page, right? And so the way you do that, and I actually wish I had mentioned this before when I talked about scraping, but Google Chrome has this great thing where you can inspect elements here, and that pops up a little box here that says sort of where in the page that thing is. So, and you can also kind of scroll up and it'll highlight the parts. And so if I keep doing that, the part that actually covers this whole container is a div with the class of sItemContainer. So if I search for all of those, I'm going to get all the item containers on the page. That'll be all the things that I want. So let's look, say the items equals root dot find all div, and the class equals sItemContainer. Okay, so let's see if there are in fact 24 items on a page. Great. Okay, so now let's start looking about how we actually get information from within this. And I'm not going to go through all of these because it's the same kind of thing each time. But now what I can do is I can actually look through each individual ones in the same sort of interface here and try to find this. So if I want to get, say, the picture, that's going to be an image tag, and the link is the source there. So if I want to get the the picture, let's just print this, or a link to the picture rather, I would say item 0, and I do this for all items, find the image, and I'm going to look at the source. So that's going to be the link to the image that I'm going to have. I'm also going to download that image later, but we'll sort of get to that in a second. If I want to get, for example, the text of the item, I can highlight that part here. So let's move down a little bit, or let's just inspect that part here. Inspect this. Looks like it is in this A-link normal class. So I'm going to look for a 0.find from the item, and the class is equal to a link. Actually, no, I don't want that one. So the link itself is actually this S-axis detail page. A lot of them are normal. That's more just like styling. The S-axis detail page is actually the type of link it is, and so that's the one I'm actually want to use. So S-axis detail page, and the text within that is going to items. The text within that is going to be the one that actually gives me the name, and I can also get the link here too. So I can get also the link of it, etc. I can get the number of reviews by looking at different parts here. I can get all of that kind of stuff, right? And this is by far the best way of doing scraping. Don't try to read the page. Just try to click on each of these elements. Basically, inspect that element there. It'll give you this. So the class that I want there is some star things, and I can basically figure out everything that I want. And so what I have in the end is I did this not here, and I want to do one more thing. So that's how you get all the items. So basically for each item here, for each 24 items, I'm going to get the text, I'm going to get the link if I want. I'm actually not going to use the detailed page link. I'm going to use the text, the image, and I'm actually going to get the image itself too. So I'm going to download the image data. I do that with another request query. I get the number of stars it has and the number of reviews it has, and the price. All right, so I'm going to get that for all the items here, and then I want to now scrape through this entire set of results. And so just like Amazon doesn't like you to use a scraping text, they actually will also throw up a similar error if you try to just edit the URL to put what page you're on. So the way you have to do this instead is you actually have to look down here at the links for the next pages, find this one here, so inspect this element here. This is going to be an element called span class equals page n link. There's going to be multiple of these. I'll just sort of just take a look at what that looks like. So this is now back in the root element, and I want root.find, where is this, span class equals page n link, and I actually want to find all of these. This will give me all the future ones, and so it gives me, the link itself here, as well as the number of the link it is. So I basically track what number page I'm on. That has a different class. I look for the next page in the list, and then I go to that link. And so I crawl the pages that way, and that works much better than trying to edit the URL names, because this is actually how it's meant to be done, sort of by a person, and so Amazon won't block you. At least they haven't blocked me yet. Okay, so this is now sort of all, I sort of did all of that, and I won't go through everything that I do here. What is, I put it all in a function that had a script that I ran on a different computer, because I don't want them blocking my computer, which they might do. Ran on some other computer, and I pickled a file that had all these things in it. So what I'm going to do now, I probably should have just did this, but let's see, equal. So what I'm going to do is I'm going to unpickle everything that I did. So I put it in this file called output.pickle. I am going to read elements from that until I have an exception. In other words, until I reach the end of the file. So I pickled first the URL and then the items I extracted from that page. This I probably should have copied from somewhere, but oh well. All items plus equals pickle.load f. And then when I'm done, this is when I hit the end of the file, I'm going to break. And I should have now a list with Length of all items. Oops. Let's see. So what am I doing wrong? Output.pickle. RB is F. Try URLs.append. Oh, I didn't import pickle. That's helpful. And so what all items is each item here is a dictionary that has the image data, the name of the thing, a link to the image, which I don't use. I just use that to load the image, the price of the thing, the number of ratings, the link, and the stars it has. So I'm going to put this now all in a data frame. And this is going to be the data frame I'm going to use for the majority of this. Okay, so basically, image data, that's going to be a JPEG. So you just see the JPEG, the raw data here. Image link, you have the name. I actually ordered it in different ways. This is not quite the same ordering as you saw before. The price, and then the review here. How many stars is out of. Okay, so that's sort of my scraping procedure. I have a data set now of, how big is it? Of 5,289 items I scraped from Amazon. It took maybe about 20 minutes to crawl the whole thing, just because it takes a little while to load each page. You have to download all the links, but it's pretty straightforward to do. And basically, just following exactly this procedure, just making them functions instead of scripts in the notebook here. Okay, so let's talk now about some sort of initial data visualization. And actually, I should call it probably cleaning and viz. All right. So one thing you saw about our data set is that the number of ratings, I was just extracting the strings here. So if I wanted these to be actual integers, and these probably to be, well, actually price is an integer the way I set it up, but these are also not floating point numbers, they're just text here. So I have to do a few sort of bookkeeping things, but these are things you have to sort of remember to do. So the num ratings is going to be equal to num ratings, and I'm going to apply the following function. I'm going to take x, but I'm going to first replace it with all the commas with nothing. So now these are all going to be floating point numbers for the number of ratings. Okay, kind of boring, but useful stuff. Similarly, stars. Oops. Similarly, stars is going to be the stars. Is everyone familiar with this and what I'm doing here? So apply is a function that applies for a given frame. I'm putting a lambda function in, so basically I'm going to replace the column with some function applied to that column. This is a very common use pattern that I do for a lot of my data munging. So I'm going to say x.split at this. I need to keep track of time here because I'm going to run out of time almost certainly. Guys, like flag me when I'm if I start going over, let me know. Okay, all right. What did I do there? Lambda stars. Oops. Did I already do that? X.split 0. Why is it a string there? That's weird.
The x is a float. It's already been replaced.
When did I replace x with a float?
Num rating says x is a float. Num rating.
But I'm doing star. Oh, right. Shoot. Let's just do this. There we go. All right. So now the stars is just the stars as a floating point, and then finally I will. Finally, stars go from 1 to 5, but since there's no 0 stars, I want to just normalize to be between 0 and 1. So I'm going to make a rating that is equal to stars minus 1 divided by 4. Just so we have a stars, yeah, divided by 4. Right. So now, and I'll maybe copy this and put it up here. But okay, so now, did I run that? Yeah. Now I have numeric ratings for all of these things. Yeah. So just notice that. We'll get to those in a second. So if you actually go through all the Amazon listing, it turns out that the things that aren't sold by Amazon but sold by other sellers don't list the price in the same way on the front page. They list in a different way. It's not that many of them, so I'm going to eventually throw them out, but there are some of these that come up. So we'll talk about that in a second, actually, about how I'm going to process that. Okay, so now let's do a little bit of kind of visualization of the data that we have. And really this is the first thing that you do once you get to data. You don't start applying machine learning. You just start trying to get a sense of what kind of data you actually have, what your data looks like. All right, so let's look at first the ratings. So let's say do a histogram of, well, let's just do of the number of ratings, actually. And I'm going to have 25 bins. Going to suppress the output there. Okay, so this is not very useful. So what's happening here is that there's a heavy tail in this distribution, right? So if you evenly divide the number of ratings, the vast majority of items don't have very many ratings at all, but there's a sort of a sum set that has a lot of ratings. And so the raw number of ratings is actually not very useful as sort of something to visualize. And so now this sort of leads to a trick that is really useful, is that oftentimes you want to, when you get data like this that's heavy-tailed, you want to log transform it. So it's heavy-tailed and positive. So I'm going to take the log, I'll do the log base 10 of this thing. And now we have a much nicer distribution of sort of the number of ratings you actually have per, or at least a much better way of visualizing the number of ratings you have per different item here on Amazon. So, you know, a small number have 3 here is 10 to the 3, so it's a small number have more than 1,000. You know, most actually have 1 review. That's the most common to have, and things like this. We can do the same things for the rating itself. So let's look at. There's never 0. So I only download the ones with at least 1 rating. If you have a 0, then you do this. If it's negative, then you can't do that. You do the absolute value or something, the 1 plus the absolute value of the thing. But that's sort of how you do it. Yeah. But since they're always positive here, I'm only counting ones that have 1 review. It's fine to just do the log of it. Okay, we can do the same thing for the rating itself. So I'm going to look at 25 bins here. And I hate when it does that. And this is the histogram now of ratings that we see. And it's also sort of heavily biased towards 1 here. So what's happening here is that there are a lot of reviews that have 5-star reviews. Now, 5 stars isn't very common, except in the case where there's only a small number of reviews, right? So what we can actually do is look at both these things together. So we can look at a scatter of the number of reviews. And probably we actually want the log again of the number of reviews, otherwise it won't be very meaningful. Ratings, I'm calling it, and rating. Plot.scatter, rating. So this sort of captures what's going on here, right? So on the right here, these are all the ones that have only 1 rating, and sorry, on your the left. And then you sort of, I mean, therefore they're only in 1 of 5 bins, right? And the other thing that happens is that as things get more ratings, the chance of them getting a 5 is less and less, right? So because, you know, once you get a little bit more evidence, then the probability of seeing, you know, the same coin flip again and again, if there's some true mean down there, is less and less. So we want some way of kind of trading off between the number of reviews there have been and the actual rating they have, and having some kind of combination of these 2 things. And what I'm going to do is it's the end result ends up being a trivial modification, but if you want to be technical, what I'm actually going to do is I'm going to use a Bayesian prior. I'm going to use a beta prior on my review there, which essentially corresponds to, I'm going to assume that for every item, there's been 1 1-star review and 1 5-star review. So that's the baseline everyone else gets, and I'm going to normalize from there. So I'm going to also add in, I'm going to add a new page, a new column called, you know, the Bayes rating, and that's going to be equal to it's going to be equal to the rating times the number of ratings plus 1. because that's my one positive review I have, and divided by then the number of ratings minus 1. Oh, sorry, plus 2. That's the positive review and the negative review there. And so this is going to be my Bayes rating, and I can do the same thing then with this here, just with my Bayes rating. And it's obviously a complete hack here, but I think it's actually kind of reasonable what it's doing here. So basically, when you have one review and 5 stars, you're no longer a 1, you're now a 0.67 because you have one negative review, one positive review, and then 2 positive reviews, right? And as the more you accumulate reviews, the more your evidence builds up, and you deviate from your prior, and you become actually you sort of approach the actual thing you have. So this is a nice way of trading off between. I mean, there's any ways you can do it. It's just a standard smoothing thing. We did, by the way, the same kind of smoothing for naive Bayes. That's exactly what we were doing in naive Bayes when we had that what was called Laplace smoothing, or for the n-gram models. But this is sort of what I'm going to do here. So I'm going to use this rating here to try to predict instead of my my like default rating, because this takes into account how many there actually were. Okay. The last thing I'm going to do is I'm going to do a couple other things. So, actually, before I do that, I'm going to look at price too. So let me look at also the price that we have. And now something's going to happen here. Something interesting happens. As you pointed out, there are some nans in the price. So we don't want to look at those that have nans in them. So I'm going to say, let's look at the ones where this is not nan. And a good way of removing everything that cannot be plotted is the pd.null. That'll return also for like not a time, if it's a timestamp, or if it's none or nan. It'll return true for all of those. So I want to look at all the ones that are not null. I'm going to look at those, that subset, and then I'm going to look at the price of those things. Now let's do bins equal 25 again. It's pd.is null, sorry. Okay, and what happens here is exactly the same thing we had with the number of reviews. So again, these are a heavy tail distribution. They're always positive, so I'm going to take the log of the price instead of the actual price and plot that. And we'll do it log base 10, just so they're a little bit more intuitive what these things are. Okay, so now this is now our distribution of prices, or of the log of the prices. So most things are, about 10, a little bit more than $10, maybe like $10 to $20. But there's a heavy tail here. There's some really expensive things, and there's some real cheap things too. Now, another question that we might have is do we care about the price at all? Is the price actually a useful feature? And remember, the idea that I want to have here is I want to predict. So sort of my goal that I set out with at least was to try to predict these ratings. And so I'm going to end up predicting now my Bayesian ratings. And I want to know, is it even worthwhile keeping this price, right? Before I do any machine learning, these are just 2 features. I want to know, is there really a correlation at all here? So what I'm going to do is I'm going to do another scatter plot where I'm plotting this thing versus my Bayes rating. And see how this looks like. Man. What was that? Right. Here. This is different order. Okay, so maybe there's the correlation here. I actually can't really see it, to be honest. I don't see an obvious correlation there. I mean, obviously, as you get more expensive, maybe the reviews get a little higher, but they just also get less dense here. I mean, there's a lot more items here, so they're going to have a denser distribution there. At the same time, though, I don't necessarily want to throw this away because there just aren't that many that don't have prices. So if I look at the total size of this thing, I have this many. If I look at the number that don't have prices, so this is sort of that would be the sum of this. Most of them do. So I have 500, 10%, they don't have prices. And so I'm actually okay throwing it out. And so I'm just going to go ahead and throw it out so I can add that as a feature. It ends up playing a small role, I'll just sort of say, in these things. But I'm going to add it as a feature. So the other thing I could do, of course, is things like data imputation, where I actually impute a mean value for those ones. But for a first pass, if you have data that only throws away 10% of your data, just go ahead and throw it away. It's fine. So I'm going to do a few filters now. So I'm going to do, I'm going to drop what's the syntax here? Subset equals price. I'm going to do this in place. And the second thing I'm going to do, I'm also going to actually sort it. Sort values as the call by equals base rating, just so I have them in a nice ordered order. I have my top ones at the top, etc. I'll also do that in place. And the last thing I'm going to do actually is drop all my items that have less than four or fewer reviews. And so this is sort of actually interesting, right? Because I said I'm kind of handling that by taking care of this by I handle these high reviews by scaling them according to this Bayesian rating, I'm calling it. But the reality is, if I include these ratings of when there's only one review, it's really most, I mean, as we saw before, right? Most the majority of, not majority, sorry. The plurality of these things actually have only one review, and the next most is 2 or 3. And so if I have all of them in my data set, I'm going to bias it towards predicting really well on those things with very little reviews, even though I've scaled them appropriately, right? And so I do want to throw those away so that I actually start doing a little bit better and start making a little bit better decisions in terms of, I don't really care how well I can predict these scores because I believe kind of they're to a certain extent random. And so I want to drop ones that don't have too many reviews so far. So the last thing I'm going to do is df Bayes or num ratings is greater than or equal, it's greater than 4, I'm going to say. So I'm going to only keep my ones where they're greater than 4.
Why do they want to do that normalization Bayesian? Why you just keep
well, so I'm still, I mean, 4 is not all of these. 4 is just up to here. These ones are the ones that would actually be really influential right there, the ones with like 10 reviews that are all 5s. Those I still don't trust fully, right? Because I don't think 10 5s is necessarily better than, if you have almost 100 ratings and have like a 4.8. I would not say you are better. So I still am sort of am normalizing here, but I'm throwing away some of the absolute kind of lower end. These are choices you can make differently. These are choices that I made in terms of sort of how I think the data set should be organized. You are welcome to make different decisions. Okay, so let's now jump right in and do some machine learning. And we're going to do it the wrong way. We're going to do what I advised you not to last time, which is you apply a fancy algorithm right off the bat and see how well it works. So now we're going to talk about doing some machine learning. And what we set out to do kind of originally was to predict these ratings given some features of the item, and that's really all we have thus far. Is we have the name of the item and we have a picture of the item. So maybe we can use both those two things, and the price, I guess, too. But those are the things we have, and let's see how well we can actually go about predicting the rating, not even looking at the thing, right? We don't even open up the page description and see what the description is. We're just going to see, from a cursory glance at the item, could I give a reasonable prediction of how well this is actually, what the rating is actually going to be. So to start off with, let's start talking about what we're trying to predict. So we're trying to predict this rating, Bayes rating, right? Bins equal 25. So here's our rating that we have. We're trying to predict this thing. And one thing you'll notice is that this, if we use something like least squares to predict this is probably a bad idea, right? Because these ratings are always between 0 and 1, and they have a very non-Gaussian distribution. They're not Gaussian at all, and so if we use least squares, maybe it'll work okay, but it'll probably also give some predictions that are kind of, above 1, and it won't capture the actual variance here, and so a least squares loss function could actually be quite bad for that distribution. So to get a better sense of what my distribution should be, this is sort of a common trick people do, is that when you have numbers that are between 0 and 1, you apply what's called a logit transform. So it's actually the inverse. So if you think about the sigmoid function, the sigmoid takes the entire number line and compresses it, as an input and as output a 0 to 1 number. If you invert the logistic function, that's called the logit function, and that is, I don't have it here, well, I can use it here, but basically you apply this function, p over 1 minus p, If you apply that function to any number here between 0 and 1, you get a number that spans the whole real line. It has to be 0 and 1 non-inclusive. You can't have things that are 0 and 1. That will throw an error there. It will be undefined. But between 0 and 1, that's anything there will work. And that will give a much nicer distribution. One way, by the way, of testing distributions, about seeing what they look like, is something called a QQ plot. I'm not going to get into that at all. But basically, it plots different quantiles of a distribution versus the other expected quantiles of the empirical distribution. And let's see, import scipy.stats. And you can do that with this function in scipy called probplot. I'm going to plot my Bayesian rating against, by default, it's against a normal distribution, and I'm going to plot that. And if the data was in fact normal, these two things should approximately line up together. And this is just sort of evidence of the fact that this, I mean, we know it can't be because it's bounded by 0 and 1. But even within that range, right, it's definitely does not look normal. It looks very skewed within that range. So I'm going to apply a logit transform. And that's going to be, so I'm going to call it a logit rating now. It's going to be the f of the Bayes rating, and 1 minus. And now I'm going to do the same thing here, and hopefully, well, actually, let's do a histogram first. Let's do this one first. So it looks much better in terms of sort of normality now. And in fact, if we do a QQ plot, what we'll see is that it is maybe a little bit skewed. You know, it's not quite perfect there, but really this is pretty good. You don't usually see QQ plots in practice that look that good. In fact, I was actually really surprised by how good that looked. Most of the time, there's, especially on, you know, when you get over here, they diverge a little bit, but that's pretty good looking. So. That, in other words, what we can kind of state is that this is an interesting fact in and of itself, I think, actually, is that the distribution of ratings is approximately looks like a normal distribution where you then apply the logistic function to that to get a number between 0 and 1. And so that's what the distribution of ratings kind of looks like for Amazon reviews, at least for baby toys, or for infant toys. No, not infant toys, sorry, toddler toys. Okay, so that's great. Maybe we want to use this now logit rating instead of our. We probably do, in fact, because it's going to be one where our losses are much better calibrated to sort of what we're actually trying to predict. Our distribution is going to be much better calibrated to what we're trying to predict. And so we're going to use this objective. We're going to try to build a least squares predictor that tries to predict this term as a function of something about the data. That's going to be our goal. So let's start doing that. Let's see what those somethings could be. Okay, so the first thing that we sort of have that I would think might be useful is that we have the price, but we already saw that wasn't that helpful. The next thing that I would think would be helpful is the actual item name itself, because even though they're kind of brief, they have some description there, and they can be kind of useful. So I'm going to use a bag of words approach and try to extract n-grams and build a TF-IDF matrix from the names of the items, and see how well I can use those to classify what rating these different things have. So here I'm not gonna do what we had to do for the homework. I'm gonna do the cheating way. So there's a nice thing called feature extraction text. From import TF-IDF vectorizer. And TF-IDF vectorizer. I'm going to set some parameters here, just because I typically use. Basically, I'm throwing away any term that does not occur in at least 10 different titles. Those tend up just not being that useful if they only occur in a handful, even if they're really indicative. Maybe 10's too high, but I'm just going to use 10. And I'm also going to throw away ones that occur in more than 30% of them, though that actually doesn't have much effect here. And I'm going to take n-grams of these things from 1 to 3. And now x TF-IDF is going to be equal to TF-IDF dot fit transform. This is going to apply the transform and output a matrix that does that. So X TF-IDF is a sparse matrix with 268 columns. There's 268 terms that occur more than 10 times and not fewer. Terms and 2 grams, right, that occur more than a certain number of times, et cetera, and less than a third of the time. And I'm going to set, actually, while I'm here, I'm just going to set my full matrix to be the combination of this TF-IDF matrix and the price. So I'm going to take the log of the price, in fact, because we know we don't want to use the raw price. It wouldn't be very useful in, say, a linear model. It's just going to be too badly scaled, so I want to take the log of that. This is actually another useful thing to mention, especially when you're thinking about linear models, so like the first class of models you have. If your features are highly skewed, they're going to be not that useful in a linear model, right? Because if most of my prices are between $10 and $20, and I have one price of $1,000, any function of that will have a huge, that 1,000 thing would have a huge impact on the actual price, and so you can't really use that. If you use decision trees, you don't have to worry about that because those just use thresholds, not absolute values. But if you use a linear model, you want to scale your features to be kind of in the right range here. Let's see how I'm going with time. I'm definitely don't have enough time to get all through this, but that's okay. Okay, so let's do this. Let's look at the price here. I think it's dot values. I need to make them an array here, and then y is going to be df logit rating dot values. What did I do? I actually want a matrix. The way I get a matrix instead of a vector is that. Okay. Now again, let's build some training sets, test sets. I'm also going to use this is easy to do ourselves, but train test split x test x y test equals train test split. Test split x and y, and let's make this test size 0.3, and then the random state equals 0. That way we sort of will break things down every time, and now I'm going to break this further one up into test training and cross-validation. Y train y CV equals split x. I meant to make that 3. Okay, so now I have my training set test set. And I'm going to do what I told you not to do, which is start trying to fit something with, of course, the your favorite fancy model you have. So I'm going to use a gradient boosting regression tree, so a gradient boosting regressor. So I'm actually doing gradient boosting on this is a regression objective. We're trying to minimize. It's a regression problem. We're trying to predict the rating. And so I'm going to just do this. I tend to call all my scikit-learn things CLF, even if they're regressors, but just it's force of habit. I have no idea what the parameters should be because I've never done any of this before. I don't know what to do. I'm just going to use the default parameters, and I'm going to fit the training data and to my boosted regression tree. Okay, so now let's look at what the actual mean squared error is, and see how this actually predicts things. So I'm going to look at the mean squared error in terms of how well we actually do. And I'll write it out here. There's a function, I forget what it's called, that does this for you. I think like score or something. I think I'm going to use score later for classification, but let's just do this. So minus y train. We want to find the mean of the squared errors. So that's this. And that's 3.37. So is that any good or not? I don't know. Is it good? Does people think that's good, that we can predict within an average mean squared error of 3.7 when I do a logit transform of the rating? Who thinks that's good? Who thinks it's not good? Okay. I would say it's actually pretty good. The way you evaluate, by the way, is you look at what you would predict if you just predict the mean value. Remember, if you didn't have any features, you would just predict, and you want to minimize least squares error, you just predict the mean. And by the way, the ratio of those two things is called the explained variance, or the unexplained. So yes, the ratio of those two things is the unexplained variance. So 1 minus the rate as the thing is the explained variance. So here, just for the sake of it, I'll do this. This. I won't do this for every time, but I'm explaining. Oops, what's going on? Oops, I meant to do tests here, or CV. Wait, no. I meant to do mean. I don't know what happened there. Just deleted it.
You printed in the
Okay, so I can explain about a third of the variance. Maybe good. I don't know. But this is, of course, on the training set, right? This doesn't tell us anything about the cross-validation set, let alone the test set. So let's do the same thing with the cross-validation set. So I probably should just write a function that does this. Now, you actually want to leave your mean prediction to be the training set, because if I train the training set, I'm going to predict the mean of the training set, not of the cross-validation set. And now, I don't do quite as well, right? So I'm predicting now, explaining 10% of my, yep. This one? No. The reason I was just saying that. So when you train the training set, you predict the mean of the training set. You don't know the y's of the cross-validation set until you actually see them, and so this is a much fairer comparison. So explain 10% of the variance now. That's sort of okay, but it doesn't really tell us much about, no one's going to publish a paper where they say we can explain. Well, maybe they will, but it has to be a really sort of hard domain if you're going to say that. If you're coming up with some new domain, explain 10% of the variance is not exactly success, as it's usually defined. So let's think about, and by the way, I can do the same thing on the test set. Now that we've X test. So actually we got a little lucky on the cross-validation set. We're explaining now 8% of the variance on the test set. Now I have to stop doing this analysis because I looked at the test set. We have to be done with this analysis at least, but it wasn't looking too promising. And so this sort of gets to the point that I mentioned before, is that before you do this, you probably want to start thinking, is this a problem that I have any chance of solving, right? And the way I typically think about doing that is I think about kind of playing a game where you are asked to classify or asked to predict the ratings yourself. So I'm going to call this, I'm going to start a new thing here called like a class of prediction game. And let's see how well we can predict. Let's just jump right in. So I'm going to make a function here that displays an item. So you actually want to see what an item is, right? So you can't just do that. You can't really look at the rows in the table and know that. You want to see the picture, all this kind of stuff. So I'm going to do this. So import IPython. Oops. Python.display as display. Display.image or display.display. Display.image s data equals s image data. So I'm going to pass a row actually from the data frame. I'm going to say what the name of the item is, and I'm going to print plus string, and I'll even round. Okay, so let's display the first item. This is actually, by the way, the highest rated one. Oops. Display item. Okay. So that tells the name, says how much it costs, and displays kind of, we're sorted by how good the Bayes rating is, and so this is a good item here. Now let's play our game. All right, and so we're going to select one that's the length of this thing. We're going to do the same thing again. Display item 1. df.iloc. Maybe we'll like print a separator or something. And now I'm going to say, oops. Now I'm going to ask us, which has the higher rating. I'm going to then say also the true ratings. I'm going to use the Bayes ratings here. Bayes rating. So that once we answer the question, we get to find out whether we were right or not. And then I'm going to, well, we can tally it. Well, let's just do it. So the correct equals, our guess is equal to 1. So that's, we pick the first one, and so that means that this one is lower than this one, because it's a sorted list, so the higher ones up are ranked. Or, well, I don't want to use that, I actually want to use ands. Or the guess equals 2. And IT2 is greater than IT1. We won't worry about them being equal. This is just. What was that? Yeah. Thank you. Otherwise, it'd always be, well, we always be pressing the first one then, and we'll press, print, and correct. If correct, else incorrect. Okay. So let's play the classification game. Let's call it classification game, just to be pedantic. All right, so here we have 2 items. Which one do you think is rated higher? So we have a Playtoys mini roller for $16 and a Fisher-Price Growing Baby Fun Sounds flip phone. Which one thinks is rated higher? Second one. We have to go faster. We're right. Okay. Wait, no. Something's wrong. The second one has a really low rating, actually. Did I mess this up? Guess equals 1, and why am I off here?
I think your qualities are backwards.
It's this. Wait. This one's backwards? The guess equals 1, which has the higher rating.
Guess equals 1, and 1 has the lower rating. You're good. That's not.
No, it does want to be lower, right? There's guess equals 1. I want the first one to have a lower rating than the second one. It here is the index in the list, which is sorted, but I'm struggling at why this is happening.
Flip the signs and see if that works.
Yeah.
Sorted from the lowest to the highest, or like.
Sorry, what's?
I think it's sorted.
Oh, I might have sorted it the wrong way. Yeah. I probably didn't do it. I meant to do this actually. When I sorted my list, I meant to do. Ascending equals false. All right, let's see. Okay, so I got one wrong. That's what it actually happened there. Okay, so we're 0 for 1 so far. What about these two? Any guess? I'm gonna guess number 2 is better. All right, so I'm right there. They're both really high though, so that's sort of a bad one to look at maybe. What was that? 2. Let's go with 2. All right, look at that. That one's really highly rated there. Okay, I actually have those blocks. I really like those blocks. No, but oh man, they're awesome. The rings actually are awesome. So, what am I? I had 50% so far. Okay, let's see. So probably I'm guessing. I also have that a popping one that's like that. So no, that one has an awful rating. So I did this a bunch actually when I was doing this, and I went through about 20 or 30 of these, and I actually am an expert at this. I would say I have a lot of these, or have seen people with a lot of these toys, and I couldn't do very well. So as sort of a general statement, just I'll let you know, I did quite poorly at this. So I was not able to. And what happened was I would keep. So some of these, the problem is these are actually both overall, these are fairly low ratings as far as Amazon ratings go, right? I mean, we saw the mean was like around 7.7 something. So there are a lot of cases where you have two things that are pretty similar. You have like two, like a 7.1 and a 7.4, and those two I just cannot tell apart at all, right? So this is kind of getting back to this point of, before you try classification, see if you can do it yourself, and I actually couldn't do this myself. I forget about predicting the rating, because that you can just always predict the mean and do kind of okay, as we saw. But I'm not able to sort these things very effectively. I'm just not very good at it. So now we get to the point where we think about changing the problem, right? This is sort of these steps of data science. We went through this first step of, well, we sort of took the wrong thing first, right? We didn't think that the problem was possible first. We sort of said, I'm just going to try something and see if it works, and it didn't work. So what do we do next? And the answer is, well, we see if we can change the problem to make it better, to make it feasible. So you can do that in a bunch of ways. I think that one option would be maybe scraping text from the description of the items. I mean, the title itself is just not that informative. Maybe you want to actually scrape each page, the description. But at least for the context right now, I'm gonna take a different approach. I'm gonna take a simpler idea. So the problem that I was running up against when I was doing this is that it was very difficult for me to differentiate between sort of two that are right in the middle, right? I think, though, maybe I can differentiate between toys that are really good and ones that are really bad, which is sort of what I care about in some respects, right? Because if I mess up and predict, that a 7.5 or a 0.75 is better or worse than a 0.71, doesn't really matter. But if I mess up and buy a toy that's really a 5, and I thought it was going to be the best toy ever, a 0.5 rather, 1 star, 2.5 stars, that's a problem maybe, right? So I'm going to think about changing my problem in a way that actually considers now just the best and the worst of the bunch, okay? And we're going to see if I can do that any better. All right, so let's change this a little bit. All it's going to be here is I'm going to now take the top 10%. This one here is going to be the same, but then plus 9 times len df over 10. And I have to, by the way, randomize them, otherwise the second one would always be the worst one. That would be easy to figure out. I'm going to swap the two. So I have it2, it1, 2 equals 2, item 1. So I'm going to swap the two. All right, let's see if I can do well with this game now. Of course, this is the mistake of doing this live, as I'm sure I'm going to get it just as bad here as the first one. Okay, but what do we think here? Which one do we think is better, an amber necklace or a thing? So I personally don't put any stock into the amber necklaces. They're supposed to help teething pain. They're supposed to have some chemical that does that or something like that. I don't put any stock into that. So I'm going to go 1 out of, even though it's probably 2 out of my own, strong intuitions there. But I was actually wrong. People love those necklaces. I had to do this out of my personal conviction, but people love those necklaces. You'll see this, I'm sure, as well. If you have a baby in America, you'll certainly see people wearing those. Okay, so let's see. So I probably think number 1 here, maybe. Actually, no, I'm gonna think number 2. Melissa & Doug is a really good brand, so I'm gonna think number 2. Okay, so I'm right here. So this first one probably has some error with it that's going badly. Again, I'm gonna go with my name brand recognition there. Melissa & Doug is a good brand, so I'm gonna go with the first one. Let's see, so best choice musical products, educational, musical. I mean, how could you go wrong with that? People love those kind of things. Look at that, I'm right again. Let's see, Rubber Duck. No, Green Toys is a really hot brand. Green Toys is like this eco-friendly brand. It's definitely this one. Yeah, see, I'm an expert at this, I told you. All right, let's keep going. You get the point. I'm gonna do pretty well at this, actually. Again, being an expert at this, right? Yes, so what's the question?
We do realize that it's not the kids who are giving the reviews, it's the parents.
Yeah, but parents love these. Oh, yeah, that's absolutely true. The kids might love the Rubber Duck a lot more. Green Toy, again, it's the parents giving the reviews of these things. But you listen to your kid. If your kid hates something, you'll give it a bad review. Okay, so now I think I believe maybe that I actually can solve this problem now. I believe there's a hope at solving this problem, whereas I don't think there was before. Even if you treated it like as a classification task, is it above the mean or below the median, say, I don't think I'd be able to solve that. I think I can solve this. I think I can differentiate the top 10 percentile of toys from the bottom 10 percentile of toys, right? So let's do this now. So let's now do the second take on machine learning. Maybe we'll actually, we probably won't finish there. So second ML take. All right. Let's do this again. So now I'm going to take only a subset of these things. Oops. So this is going to be the ones that have the rating is going to be greater than the percentile of the Bayes rating. Let's say so it's either greater than the 90th percentile or it is less than the 10th percentile. So I'm going to subselect only those ones that fall into that range. And then y is going to be now, I'm actually also going to consider now, instead of just trying to predict, I mean, those are all high scores or low scores, so there's no real point in trying to predict the scores of a regression task anymore. I'm just going to consider this as a classification task of can I predict if it's a top toy or a really bad toy. And by the way, you shouldn't really be doing this because when I'm predicting on new toys now, I'm not somehow magically able to discard all but the best or the worst, right? What you really should be doing is thinking about training on everything, but having some cost associated with each example, depending on how far above the median or below the median it is. That's a much better, sort of more disciplined way of actually doing this. But for simplicity, I'm just going to consider this, and then we're going to apply it to the case of all the things, even though know that that's actually not something you really want to do. You probably should have all your data, have all the examples, just downweight those in terms of their importance for the ones that occur in the middle. But I'm going to know that I should be doing that, but I'm still going to do it this way from what I see right now. Okay, so we're going to have the label just is the Bayes rating better than the median of the Bayes rating. Okay. Do the same thing with test set and training set. Let's try to see if I can copy that. And now I'm going to do again the thing I shouldn't do, which is well, actually at this point you can probably do it. Gradient boosting for something this size. These are pretty small. Once I filter this down enough, this is pretty small. So we're talking about. Oops, what's going on here? Oh, I just made all of them. I'm going to take only those. Billion, what's it complaining about now? I guess I want values. Okay, so this is pretty small now. I have 200, 300, a small size training set, but this is actually not awful. I mean, for a long time, people did boosting and all these things with data sets of 100 or a couple hundred, and it's fine. So we're not talking about big data here. Certainly, I probably want to do the thing where I actually downweight examples, but you know what? This is one type of category, and it's going to let me run things fast enough to do the stuff that I want to show. So I'm going to do a classifier now, and gradient boosting is a perfectly reasonable classifier. Load it. Let's fit it to the data. X train, X, Y train, and let's predict. Or let's see what the score is. The score is just here going to be accuracy. X, CV, Y. Okay. So, oops. So this looks a lot better. Right, so now we're talking about classification. We know that the baseline is around 50%. It's not quite because I didn't do stratified training testing splits. So it's going to be approximately half of each class in the test set, it's a class-validation set. And so, now we're obviously still doing much better when it comes to training error, but we're doing reasonably well now. Our classifier is getting 70%, approximately 70% accuracy in terms of differentiating which are the best toys and which are the really low-end toys, which is probably, I might do a little bit better than that, but probably not that much better than that. some of the things I can do better might just come from my visual look at these toys. That that's going to be hard for a classifier because we don't have any images there yet. This is so far just the text right now, right? That's also important. We're just looking at the text so far. I don't know if I'll have time to get the images. We'll see if we do. Okay, so now what we want to do is now we're at a point where we can start doing this. This is okay. In fact, this is maybe as good as we're going to get. But now we can start doing the second, step 2B that I talked about last time, which is saying now we want to start analyzing and debugging the performance of these algorithms. And we do that by running diagnostics that show the various performance, show kind of the classification performance by over different things. So the first one I mentioned was the plot that was very useful to draw is plotting the error. Actually, I talked about plotting the loss. I'm just going to plot error here because it's roughly the same for this case at least. So a plot of the error versus the number of samples used for training. Now we don't have a ton of samples, but we can still use some. So I'm going to sort of write a quick function here that lets me do that. Let's see, y, c, and the number of samples. I'll just put n. So I'm going to fit the thing to this. But only up to the number of samples that we are allowed. And then I'm going to return an array of scores, score of this thing. And x, z, y. Okay. All right. And now I'm going to think of a bunch of number of samples. So let's say my samples is going to be in x. Let's vary this from like 10. You can't start with too little. If you start with too little, then you won't be able to do anything, and there probably isn't even one of each class. So you want to have at least some. Maybe 20 is actually a better amount. And then up to x train. And I'll take like 10 steps between there. So I'm going to evenly divide that the range by 10, convert it to integers, and there's a number of samples. And now my errors is going to be of get error samples n, well, CLF x train, y train, x, y CV, n for n in n samples. And I'm going to plot the number of samples, errors, 1, that's the training error, or really it's actually the training accuracy. I should call these accuracies. Sorry about that. Whatever. It's force of habit. This should be 0. Okay. This is going to take a little while, but not too long. What's going on there? No, yeah. So remember we talked about kind of what these things should look like, and with little data, basically there's the training error, the training error is always best with little data because you have only a little bit of data to fit. You're going to fit that. Testing error is going to be lowest then, and you're going to start improving. And so the things you can think to do here are, here's a case where maybe, I don't know for sure, but it looks like we might be overfitting to this data, right? We have really good training set, really good training performance, but not very good test performance, or maybe it's actually good enough. We don't really know what the level is here, whether it's good enough or not. And so this is a case of high variance, right? We're making predictions that just aren't really, they're very good in the training set, but it's not really capturing the test set. And so it's something we can do, and I'm definitely not going to finish now. So maybe I'll actually keep this going next time if people find it useful, and I'll spend the first 30 minutes next time doing this. What we can do here is actually start varying the complexity of the classifier to bring down the complexity, make it less complex, with the hope that even though we bring that thing down, this thing might come up. Okay, and so we're going to do that. And there's a few sort of knobs you have to tune when it comes to gradient boosting. And I'm not actually going to train it anymore. I'm going to set the the setting. So n estimators is the number of trees you use. By default, I have to know it's 100. Let's use 50 instead. And the max depth is normally 3. Let's do 2 instead. And let's plot what that looks like. So we've succeeded, fortunately, at bringing down our training performance, but we did not actually improve our test performance at all. So it's sort of discouraging. And actually, I wanted to mention this particularly because this is actually the more common thing you will see. You will not see this sort of beautiful. In theory, you have this beautiful case where whenever your training performance is better than your test performance, you should lower the reduce the complexity of the model, and then your test performance goes up at the same time. That's not what really happens in practice. What happens in practice is your training error just keeps getting worse and worse, and your test error kind of just doesn't move at all. And that's very, very frequent that happens in practice. And so what you do there is actually not at all obvious, the things you can do. So remember, the other thing I mentioned was that the other option you can have is you can decrease complexity by changing the features. Or potentially by using a different classifier that's inherently more simple, right? So you can either change the features or use a different classifier that maybe does not have the same problems as boosting, is less prone to overfitting anyway. So that's what I'm going to do. I'm going to instead use now logistic regression as my classifier, and we're going to see how that one does. So, linear model, import logistic regression. I'm going to use the default parameters here at first, and I'm going to do the same thing here. And look at that, it actually does better, amazingly enough. So we actually are doing better than we were before, just by inherently using a simple classifier. And what's impressive here is that actually logistic regression here has higher training performance and testing performance here. This is not a common thing. You'll actually not see this that often. And so I'm mentally mentioning it here because I was surprised by this a little bit. It seemed kind of strange to me. What's actually happening here, frankly, is that there's just a relatively small data set we're talking about here. And so it turns out that in this data set, the hypothesis space of on this random cross-validation set, which has not very many examples. How big is the Right, it has 120 examples. For whatever reason, on that data set, it seems like a linear classifier is actually working better than a decision tree or mixed decision tree classifiers. Which, again, I mean, with enough data, the latter will definitely the gradient boosting will definitely do better because it's a richer function class. You can represent a lot more with it. But in the absence of that, in the small data regime, there really is anything goes in terms of the ordering of these things. That's not indicative of their actual sort of real performance. It's just the fact that when you have limited data, your hypothesis function and the random choices you make in terms of your class do actually have an impact. So do not take away from this that logistic regression is better than boosting. Just take away from the fact that for a very small sample size here, this class happens to work better at this problem than other ones. It seems like the actual hypothesis class might be more linear, or at least the thing you learn with a small data set tends to work better on some new points. Does that make sense, kind of what I'm talking there? It was a little surprising to me to see it, and it does do better. And that, by the way, I will just say that also translates to the test set too, so that actually does hold. It will hold, preview. But it's not a general statement. It is a statement of saying what happens in a very limited data domain. Okay. So now we know that we want to use logistic regression. Now we want to do things like hyperparameter tuning. So we want to tune, what should my value for my regularization parameter, my regularization parameter be for logistic regression? Should I use L1 or L2 regularization, these kind of things? And so I'm going to have another kind of function like this, where and by the way, scikit-learn has this one here. I'm just going to show how to do it. So here I'm going to actually call this the C parameter. Remember, logistic regression has a parameter called C, which is the inverse of the lambda that I use. So C is a term that, it's 1 over the lambda parameter. And I'm going to set C to be equal to a variety of things here, and we'll see how this works. Okay, so let's make C big C. The other thing to keep in mind is you want to vary regression parameters logarithmically, not linearly. They have a very big range. It's really hard to know what the range should be until you actually do it. So let's pick a big range. Let's use a log space of 10 to the -3 and 10 to the 4. And let's do maybe 50 within that range. I think that's what I did here. So now, let's do little c. And I called it like get error hyper or reg. Oops. And of course, I'll also plot it on a logarithmic axis. Okay, so here's what our plot looks like. So as we sort of, we actually got really lucky. The default is 0 there for scikit-learn. This is one of the cases where scikit-learn actually did pretty well off the bat. But this sort of makes sense, right? So remember, regularization, C is the inverse of regularization. So that means big C means low regularization. So that means you're basically just trying to fit the points exactly. We, by the way, have more features than we have data points, so we're going to hit 1 at some point, right? We're going to get 0 training error at some point, but of course not very good test error at that point, or cross-validation error at that point. And there's some, and at this side you have basically the null hypothesis, so you're predicting everything to be the same, which gets about 50% error. And there's definitely a nice spot in the middle there where we're getting about 75% error here. So let's just, that looks good. I think we're, for the first phase at least, we're getting 75% performance, at least in our cross-validation set. Let's see how we do in our test set. Probably not going to be quite as good, but because we're, of course, always overfit to the cross-validation set. But let's run that one more time just to see. Let's see. Let me take these. So C, let's pick C at like 0.8 maybe. That's like, looks like a little bit better than 1. We learned something maybe from our cross-validation plot there. And let's also now look at our test set. I could, by the way, retrain on both training. I could retrain on my training and cross-validation set to look at the test error, but it doesn't make that much of a difference. I'll tell you, it won't make much of a difference. We're doing pretty well here. We have 75% accuracy. That was better than our gradient boosting did when we first took things off the bat. I'm satisfied right now with our performance here. Okay, we have 4 more minutes left. So in the 4 more minutes, I'm just going to mention the next thing I'm going to do. So far, we've just talked about using, this looks reasonable, at least number-wise it looks reasonable, but I want to actually see more than just saying the sort of a raw performance number. What is it actually doing? What's it basing its decisions on, right? So this is actually a really important part of machine learning. Don't stop when you have a good number. Try to figure out what the classifier is actually doing to get that performance. And so the way I'm going to do this is I'm actually going to look. Remember, our features here are kind of nice because they're all words that occur. It's just really just a bag of words. It's also a price, but mainly it's a bag of words approach. And so they're all words that occur in this thing. So and I have a linear model now. So if I look at the words and their weight, it will tell me, does that word indicate higher probability of being a rating, or does it indicate lower probability of being a good toy? And so the way I'm going to do this is I'm going to get first a vector of my feature names. And this is going to be, the way I do this, I'm going to create an array of these. The call is tf-idf. You can get the feature names of this. And then there's one more, which is the price. And oops, this should be. So those are my feature names, and then I'm going to sort. Well, first I'm going to sort of do a zip of the feature names and the classifier, the coefficients. The coefficients are for some reason in a matrix, so the 0th element is the vector of coefficients. This will give you sort of all the things and their associated. All the words that occur some number of times and their associated weights. But I want to sort them by their absolute value, say, so I know which ones actually have the most impact. At least in the TF-IDF sense, right? There's also weighting for the TF-IDF, but to a first approximation, the weight here can be a good proxy for these things. So I'm going to sort these things and I'm going to sort them by their absolute value of the score. And I'm going to reverse it. So they are, in fact, there. So I'm going to do this, and I'm going to take a look at like the top 20. OK, so this is really interesting. I didn't expect these. Something's actually strange here. I think we're actually reversed. We somehow reversed the classes up top. Did I actually reverse them? I think I know that doesn't make any sense. So I'm guessing that I actually somewhere reversed these. I suspect actually what's happening is that it's chosen sort of arbitrarily which class to put, and so it's picking things that are, it's made the positive class the ones that have bigger score and negative class the other way. I can verify that next time, but these green toys I know is a great brand, so that should, and so is Melissa and Doug. You know, it's one that had lots of high ratings, and so it shouldn't be doing it that way. They're all interchangeable as far as scikit-learn is concerned. Doesn't know which is the positive class, which is the negative class. So let's see. Actually, do I have? I forget how you specify which is the positive class. Anyway. Yeah, so I can just do that. That's kind of cheating, but yeah, or just negative, right? Okay, so this is, I believe, correct. I can verify that by the next time, but I'm pretty sure this is correct. Basically, with these terms, you see them. So I don't know. Oops. Oh, I have lunch coming up next. Look at that. Let's see. Where is my other window? These terms indicate higher probability of there being a good toy. Other terms indicate lower probability of being a good toy. And so what you see here is actually what's happening is something very similar to what I was doing when you saw me doing these things. I know that so a lot of the things there, there are things like musical is actually a bad thing here. Bath is also a bad thing. People hate bath toys in general. I don't know why, but all bath is, if you see the bath in it, it always ends up having a lower review. If they call it a toy, it's just sort of asking, like forcing the point, right? So that's a bad thing. Though toys is a good thing. Some things here are strange. Who knows? But a lot of the brands here appear. So Brio, Playskool, Ballistic. So a lot of the known brands are appearing here, which is actually very much in line with how I was doing things. Right? So I was looking for sort of brand names and sort of saying, okay, I know this one. I know it's pretty good, and for the most part, these are good brands. We can look at the end too. Actually, no. So we should be looking at the ones that are most negative. There may be some brands that show up that are really bad. So I think this might be a brand that I've not actually ever heard of that. So maybe that's why it's showing up there. But it's doing something kind of pretty simple here, right? Yet, which at the same time is getting 75% accuracy in classifying the really good toys versus the really bad toys. So this isn't maybe the most fascinating thing, but it's saying something about this data that I think is actually quite interesting that I wouldn't have known before. That really the thing that's in the data, to the large extent that determines the ratings, are in fact the brand names. So far we have just used, I'm going to end here for now. I will start again a little bit next time. I'll do a little bit of the rest of this next time. But I've only used the text so far, right? And I definitely also, for good reason, I hope, downloaded the images too. So next time we're going to add images. We'll see how that does. Then we'll see how the combination of these two things do, or see images by themselves, the combinations do, and then finally deploy this to find the best toys that don't have many ratings yet. Okay.